welcome to Calculus. Today we are looking at section 5.6, definite integral substitution and the area between curves. So if you haven't already, I would really recommend that you go back and watch the video that I put out for section 5.5 where we talked first about substitution, because we're going to be using a lot of those same ideas here. So let's get started. We have a theorem here that we're going to start with that just gets us going with this definite integral substitution. It says, if g prime is continuous on an interval ab and f is continuous on the range of g of x, which is equal to u. So basically you have a couple of continuous functions. Then the integral from a to b of f of g of x times g prime of x dx. Now first, but I'm going to pause for just a second before I talk about this part. Just notice that this is the same setup that we had in the last section when we did indefinite integrals with substitution. Okay, the difference is now we have our limits of integration, a and b. But here's what happens. We can change the limits of integration to g of a and g of b, that inside p's. And if we do that, we never have to plug u back in. That's kind of the takeaway from this. Now, could you just plug u back in and keep a and b? Absolutely. But we're going to look at it as we're going to change our limits of integration to match u, and in some ways it'll make things a lot easier. So let's go ahead and get started. We'll do a few examples, and eventually here we'll get to area between curves too. All right, so here's my example for how this definite integral substitution is going to work. Here it is. So I have the integral from -1 to 1 of 5x to the 4th times the square root of x to the 5th plus 1 dx. Now from the last section that we looked at, I think the obvious choice here for substitution is going to be that x to the 5th plus 1 inside of the square root. And sure enough, if we set it up with u being x to the 5th plus 1, du then is 5x to the 4th dx, which is going to work out really nice, right? We're going to get a u under the square root here, and the 5x to the 4th dx is all going to turn into my du. Now, before I go on and rewrite it, which you can see I did here, before I do that, I want to take a second and change the limits of the integration. So if x is -1, my u would be -1 to the 5th plus 1, which works out to be 0. And if x is 1, u would be 1 to the 5th plus 1, which is 2. And so what we can do then is we can just do this integral, and we can do it with respect to u. We don't even have to worry about x ever again. I do the integral from 0 to 2, because that's me changing my limits of integration, times this, or of the square root of u du. And so I change my square root to a u to the 1/2, and I integrate. I raise the power by 1, which gives me 3/2. I multiply by that reciprocal, and now I just have to evaluate it at 0 and 2. So I get 2/3 times 2 to the 3/2 minus 2/3 times 0 to the 3/2. The second part is very nicely going to end up being 0. 2 to the 3/2 ends up being the square root of 8, because 2 to the 3rd is 8, and the 2 on the bottom makes a square root. You could pull a 2 out of there and have 4/3 times the square root of 2. I'm really not terribly picky there. But there's our answer, 2/3 times the square root of 8. All right, let's look at some more stuff. All right, so we have one more thing before we get into the area between curves. We want to talk briefly about symmetric functions. Symmetric functions are nice because their integrals can be made easier. Let's put it that way, especially the odd ones that we'll see here in just a second. They're hiding right behind me. So with an even function, remember an even function has symmetry across the y-axis. What that means is that for even functions, if you take the integral from -a to +a, like I've kind of drawn out here on the graph of a function, it's just equal to twice the integral from 0 to a of f of x dx. And that's because we have that symmetry. Basically, the area under the curve over here on the right has to be equal to the area under the curve over on the left. And so 3 cheers for symmetry. So we can simplify the integral just a little bit if we have this case, because let's face it, who doesn't like 0? We all like 0. All right, for the odd case, it's even easier. Odd cases have rotational symmetry. So what that means is, if you look at my graph here, it's probably a sine curve. It's got a piece that's in the first quadrant, it's got a piece down here in the third quadrant, and they're exactly the same size. But because they're exactly the same size, and one is positive and one is negative, if you take that integral from -a to +a, of f of x dx here, you just get 0. The two parts cancel each other out. So if you get an odd function, that's really nice. All right, let's look at area between curves. So here's the setup for area between curves. You can see I drew a graph here. I have two functions, f of x and g of x, and I'm looking to find the area in between those two things, in between a and b on the x-axis. So we have, pretty normal little setup. We have an interval from a to b, but now I'm working with two curves instead of one. Well, here's the really nice thing. If we just ignore g for a second, we could, hopefully, anyway, find the integral, find the area under the curve here with f of x. We could do the same thing with g. We could find the area under that curve. And guess what? If we just subtract those two things, we get the part that's in between. Now, I can hear some of you maybe asking the question, what happens if g of x is underneath the x-axis instead of above it, right? Because this is a pretty nice bit of subtraction. We have f of x all the way down to the x-axis minus the part that's under g. Well, if g is under the x-axis, its area would be negative. And what happens when you subtract a negative? You end up adding. And so since we're adding, what you would really be doing is adding the part that's above to the part that's below. And those would both be positive values then, because we have that minus sign in front of the g then to flip it to addition. And so it would still work. All right, so here we go. I have this all written out. The area from a to b is going to be just the area. Well, it is from a to b. It's going to be the definite integral from a to b of f of x minus g of x dx. So let's look at an example. All right, so here's my example that I'm going to do for areas between curves. I will say it's usually pretty helpful to try and get a graph, at least in your head, so that you know, first of all, which one's on top, which one's on the bottom, because you want to do the subtraction in the right order. Here's a hint, if you get a negative number, you probably did the subtraction backwards. But you can get the graph by drawing it. If you know what it looks like, you could put the equations in your calculator and graph those and see what this area is going to look like. But it really is helpful to have an idea of what you're looking at. And that would be especially true when you get into, if you take Calc 2 and you get into volumes of revolution, and yeah, those are fun. Anyway, here we go. Let's find the area between y equals 1 and y is equal to the cosine squared of x from 0 to pi. So here's the thing. We know that cosine only goes between -1 and +1. So 1 is going to be the graph, the y equals 1 will be the graph that's on top here, and the cosine squared will be the one on the bottom. And so the graph ends up looking like this. It's kind of a fun little shape. And importantly, cosine is 1 at 0 and -1 at pi. And if you square -1, you get 1 again. So we actually have equality here at either end. But we're going to just take the integral, or we're going to find the area. It's going to be the integral from 0 to pi of 1, that line on the top, minus the cosine squared of x dx. Now, we have to do a little bit of rearranging because we do have this cosine squared. And so we're going to use a trig identity that's in the back of your book. So cosine squared is equal to 1 plus cosine 2x over 2. And then I'm going to split that fraction apart. So I get 1, I get a minus half, and then I get a minus 1/2 cosine 2x dx. Now, obviously at this point, I've run out of room on my board. So keep all of this written down. I probably will bring this one back. But keep it, write all this down and come back here in just a second after I rewrite the board. All right, so let's continue on. I just rewrote the last step that we had. The only difference is we had a 1 and a minus half. I just put them together to make a half. So now I'm looking at the integral from 0 to pi of 1/2 minus 1/2 cosine 2x dx. So now I'm going to do my substitution because I can't work with that 2x inside of the cosine. So I'm going to make u be 2x, and du then is going to be 2 dx. Remember, don't forget that dx. Now, we don't have a 2 here in front of anywhere, really. So what I'm going to do instead is make dx equal to 1/2 du. That's going to make that a 4. All right. So when I do that, sorry, a couple little mistakes here. So when I do that, I can make my substitution. I get the 1/4 for both of these because I have this extra half from the du. So I just multiply both parts by that half. I could have stuck it out front. That would have probably actually been even easier. And then I change the limits of my integration. I mean, when x is 0, you plug in 0 and u is 0. And if x is pi, u is 2 pi. So now we integrate this thing. We had a quarter here. It turns into a quarter u minus cosine. Its antiderivative is sine. So we get a minus 1/4 sine u. And now we're evaluating from 0 to 2 pi. So I plug everything in. And what do we end up with? Well, 1/4 times 2 pi is pi over 2. But very nicely, everything else here is 0. Sine of 2 pi, that's 0. So that piece drops out. Half times 0, obviously 0. That's gone. Sine of 0, also 0. It drops out. So the only thing left really is that first piece. And we get an answer of pi over 2. So there you go. That's areas between curves. Have fun. Okay. They can be pretty messy and do all kinds of weird things. So good luck. And thanks for watching the video.